In the fundamental theorem of calculus part 1, we have seen that there is a relation between derivative and integral. Specifically, they are the opposite operation of one another, essentially. But we have also heard that somewhere before, specifically back in section 4.9, antiderivative. So, the antiderivative and the derivative are also essentially the opposite operation of one another. What that means is that there must now be some relation between antiderivative and integral. And that relation is going to be given in the fundamental theorem of calculus, part 2. Part 2 of the fundamental theorem of calculus states that if f is continuous on a to b, then the integral of f of x dx from a to b is going to be big F of b minus f of a, where f, big F, is any antiderivative of f. What this is essentially saying is that the integral is the same as the antiderivative. There is a subtle difference based on how you define what is an integral and what is an antiderivative. But really, for this theorem, you can think of it as being the exact same thing. And I just want to note one more thing, is that f can be any, big F can be any antiderivative of little f. Because when you subtract, when you consider big F of b minus big F of a and subtract, the constant that you choose is going to cancel out. So we can pick any antiderivative. We don't care about the constant in this case for a definite integral. So let's get to some example. You want to find the integral of e to the x dx from 1 to 3. Well, then we ask ourselves, what is the antiderivative of e to the x? Well, what function do you take the derivative of? Well, what function do you take the derivative of to get e to the x? In this case, it's just going to be e to the x itself. Meaning, the integral of e to the x from 1 to 3 is going to be e to the x evaluated from 1 to 3. This is just a notation to tell you that you are going to take e to the x where you replace it with 3, and you are going to subtract the lower limit of integration. And well, that's just it. That's what the fundamental theorem of calculus part 2 is stating. Do note that you have to make sure that your function satisfies the condition for you to use this thing. It have to be continuous and all of that stuff, whatever is in the hypothesis. Let's do another example. We want to find the integral of x squared from 0 to 1. What is the antiderivative of x squared? Well, if you look back at 4.9, the antiderivative of x squared you add 1 to the exponent, and then you divide it by the new exponent. And so x squared, the integral from 0 to 1, is going to be x cubed over 3, evaluated from 0 to 1. meaning you plug in 1 over 3, and then you subtract the lower number. So you plug in 0 over 3, and all of that is just going to be 1/3. And it really does not get any more complicated than this. Finding the integral, you find the antiderivative, you plug in the upper limit of integration, and subtract the lower limit of integration. The integral of 1 over x from 3 to 6, so you ask yourself, what function is the derivative 1 over x? In this case, the function is going to be natural log of the absolute value of x. Evaluated from 3 to 6, meaning we plug in the 6, we minus plug in the 3. And if you have a bigger function, not just any single term, for example, -1 to 2, x cubed minus 2x dx, ask yourself what is the antiderivative for each of the terms. So for the first term, add 1 to the exponent divided by the new exponent, add 1 to the exponent divided by the new exponent, and then evaluate from -1 to 2, meaning we plug in the 2, and nope, still plug in the 2. That's the top value, minus plug in the lower limit of integration, 2 -1 squared over 2. Simplify all of that. This one you should get, let me scroll down just a little bit. This one is going to be 4 minus 4 minus 1/4 minus 1, which is going to be negative 1 minus 1/4 minus 1 is going to be 3 over 4 negative. So it's just going to be 3 over 4. Remember, when you are evaluating these things, you are plugging the number into the entire function and then subtracting the function. So we plug everything into this function, we plug the 2 into the function, and then we subtract what happened when we plug in the -1 into the function. Okay, next one. Let's find the integral from -2 to 2 f of x dx, where f of x is equal to 2 if x is between -2 and 0, x minus x squared if x is between 0 and 2, sorry, just equal to, no equal to. So let's write out the integral. -2 to 2 f of x dx. Well, we can split this integral up according to the restriction given on x. Meaning we can split this thing up from -2 to 0, f of x dx, plus the integral from 0 to 2 of f of x dx. because this is a piecewise function, we can split it up and we can just take the integral of the individual pieces. The first piece, well, from -2 to 0, it's just a constant function. From 0 to 2, the function is 4 minus x squared. Then we find the antiderivative. The antiderivative of a constant is just going to be the variable, in this case 2x. Evaluated that from 0 to 2. From -2 to 0. Plus the integral of 4 minus x squared is going to be 4x minus, add 1 to the exponent divided by the new exponent, evaluated from 0 to 2. So 2 times 0, and then if we plug in the -2, it's going to be a minus -2. Plus, we have 4 plugged in 2, minus 2 cubed over 3. That's the top, minus 4 plugged in 0, minus 0 to the third over 3. And then we just simplify. Here is 2 times 2, so that's 4. Plus, in here is going to be 8 minus 8 over 3 minus everything that's going to be 0. So 12 minus 8 over 3, which is going to be 36 minus 8, which is going to be 24 over 3. 28 over 3. And that's the solution. For this problem, what is wrong with the following integration? We are integrating 1 over x squared from -1 to 3. So then, well, you would ask yourself, what is the antiderivative of 1 over x squared? And then you would find that it's -1 over x. But why is this wrong? That's the question. What is even wrong about this problem? Well, let's take a look at the graph. We know how 1 over x squared looks. There's an asymptote at 0. And if we go continuously to the right, the bottom is always positive, meaning the right-hand side should look like that. And if we go all the way to the left, it's still going to be positive. So the left-hand side should look like that. So the integral, the area underneath this curve, should be positive. The area underneath the curve from -1 to 3, it should have a positive area. But the solution that we got is negative, meaning the area should be somewhere down here below the x-axis. Why did this happen? The reason is because 1 over x squared is not continuous on -1 to 3. So you cannot apply the fundamental theorem of calculus part 2. Later on, we just call it fundamental theorem of calculus. I'm going to leave off the part 1 and part 2. Because if we look at the graph, 1 over x squared, we see that there is an asymptote at 0. So therefore, it's not continuous, and therefore you can't apply the fundamental theorem of calculus. Now let me just give one last word on the fundamental theorem. Let's just combine everything into one theorem. So suppose that f is continuous. Again, that continuous property. If you don't have that, you cannot apply this theorem. So be careful with that. Suppose that f is continuous on a to b. The first part states that if g is equal to the g of x is equal to the integral from a to x of f of t dt, then the derivative of g of x should be just the inner function evaluated at x. 2. If we have a definite integral from a to b of f of x dx, then we can find the solution by finding the antiderivative.